Let's now look at the ordinary annuities. This is more like your loans. So the difference between annuity due and the ordinary annuity is when you make the payment. So one was at the start of the compounding, one's at the end of the compounding. Right. So future value becomes this, P plus PR plus PR squared, and so on, which we know, well, it's a geometric series, so we plug it into our geometric formula. So it's slightly different. P is still the principal, R is still our 1 plus the interest rate, and so on. So the difference is, of course, with this first one, you'll notice that there is no interest rate applied to it because it's made at the end of the compounding period rather than the start. It also means the last one becomes n minus 1 instead of n because it's in there for one less time period. But other than that, it's pretty much identical. So if we then had to work out the present value, playing around with that, we would end up with this expression. Okay, so let's actually look at some loan repayment questions. The amount still owing after n time periods is always going to be this. The principal with the interest applied minus the instalments with the interest applied. Just that one key idea. And from that, we should be able to work things out. So let's use this example and explain what I mean. Richard and Kathy are going to borrow $20,000 to go on a holiday. Interest at this stage is 12% per annum, compounded every month. They're going to start repaying the loan 1 month after taking it out, and their monthly instalments are $300. So the question is, how much will they owe the bank at the end of 6 years? So we work out the initial amount. What is the compounding on the principal plus the interest? Now we're talking about for 6 years here, so that's 72 months. So principal, apply the interest 1.01 to the power of 72. Now the repayments you can consider as an investment in your loan, okay? Because basically this is what is happening. Okay? The bank is lending you money. It's like they're making an investment. It's like you are the bank, but they've given you money, okay? And then it has interest rate applied. But then you give the bank money and interest applied to that. And that's why there's the difference between the two. That first repayment then, that I'm going to give the bank, so I'm going to give them the bank, and they're going to put interest on what I'm giving them. So it's like I'm making an investment now. So that will be in there for 71 months. My second repayment, well, I'm investing it with them for 70 months. And so on and so on and so on until the second last repayment will be when there's 1 month to go. So interest rate will be applied. And then the very last one, well, there's no interest rate applied because once I've given them the last repayment, thank you, we're done. Now, hopefully what should happen is the two balance out. And so there's a zero balance at the end of it. So for our one, though, it's not paid out yet. It's going to be the principal plus the interest minus the instalments plus the interest. So the initial loan that I took out, compounded in there for 72 months, minus all of those investments that I made by giving the bank $300. Well, the one that I made is a geometric series. So first term 300, ratio 1.01, number of terms in there is 72. So we can plug that into our formula, and then we just got a few calculations to do, and we can say, $9,529. So that, how much they still owe the bank, because that's the difference between the amount the bank's invested in me and the amount I've invested in the bank. Or Richard and Kathy, I should say. So how much interest then have they paid in those 6 years? $300 repayments and 72 of them. So $21,600 they have given the bank. But the loan has been reduced, and so there's $10,470.99. So hang on. I've given them $21,600, but my loan's only been reduced down $10,470. Well, that difference then must be the interest I've paid. That's the extra money I've given them. So what do we end up with there? $11,000, a bit over. What about if we had to work out the instalments? So we know all the other ones. We're trying to work out how much do I have to pay? Right, how much will my instalment be? $30,000 to buy a car. Going to repay the loan in 5 years, monthly instalments. 9% per annum is going to be the interest. How much will we pay off each month? So that's what we don't know. That's what we're trying to work out. What's the monthly instalment? back in. So the initial amount, that initial investment, the bank is making with me. So $30,000 they're giving me, and the interest rate I'm giving them is 9%. Okay, my first repayment, my investment in the bank, will be there for 59 months. I don't know what M is, so I don't know how much I'm investing yet. But my second one will be in there for 58 months, and so on and so on and so on. The second last one will be in there for 1, and the last one obviously in there for 0. Their investment minus my investment. So this time we don't know the first term, that's what we're trying to work out. Subbing into our formula, but of course we know that at the end of the loan, amount 60 should be 0. It should balance out. So therefore, there's the equation we have to solve. We have to make M the subject. Playing around with all that, eventually, there it is. So $622.75 is what we would have to pay. Well, what about we know how much we want to pay back, so we know we've worked out what we can afford to pay back. We know how much we want to borrow, so how long is it going to take me to pay it off? Let's work out the length of the loan. Here's an HSC question. All right, so Wheelbarrow Back Council borrowed a massive $3 million. Annual interest rate, 12%. The debt's going to be repaid, annual repayments of $480,000, and the first's going to be at the end of 2005. Let AN be the balance owing. Show that. So in other words, the amount that's left after 2 repayments. Okay? Well, that initial investment, that's going to be in there for 2 years now. Apply the compound interest on that. Then they're going to make 1 repayment that'll be in there for 1 year, and then 1 repayment that'll be at the end of the 2nd year. So principal plus interest minus instalments plus interest, we get this. Well, not quite the way they had it. They've got it in scientific notation, but that's easy enough to fix up. And we have what they've asked for. Okay. Show that amount N will end up being this. So N years, we don't know how long this time. So it's just to the power of N. First repayment will be in there for N minus 1 years, and then N minus 2 years, and so on and so on and so on. Principal plus interest minus instalments plus interest. There is the expression. Well, not quite what they want me to show, so we're going to have to play around with this a bit. Sub it into our geometric formula, still not quite there. Fortunately for us, 480,000 divided by 0.12 works out very neatly to be 4 million. So in fact, if I expand that out and collect like terms, we have a common factor of 10 to the power of 6, and we get what they want. So in which year will Wheelbarrow Back Shire Council make the final repayment? Well, that'll be when amount N is equal to 0. We just got to solve this. Make N the subject. Log both sides. And we get 12.2. But they said in which year? So that'll work out to be 2017, the 13th repayment. So I think when I answer something like that, I'll put it's the 13th repayment, just in case I muck up my maths. Is 2017 the right year, or is it 2016? But at least I can say, yeah, no, I know which year it is. I just couldn't work out what the actual date of that year was. Okay, 2020. Tina inherits $60,000 invested into an account, earning interest at 0.5%. So this one is they're actually investing rather than borrowing. But it is actually a repayment question, because now we're saying each month immediately after the interest has been paid, Tina will then withdraw money. So it's like the same sort of idea. To help you out here a bit, the amount in the account immediately after the nth withdrawal can be determined using a recurrence relation. So a different way of looking at it. So amount N will therefore be, apply the interest to what you've got, take away 800. You're going to withdraw $800, where N is 1, 2, 3 and so on, and the initial amount is 60,000. Use that recurrence relationship to find the amount of money in the account after the 3rd withdrawal. Well, we just keep applying it, I suppose. So amount 3 will be amount 2, interest rate applied, minus 800. Then amount 2 will be amount 1 with the interest rate applied, minus 800. But then amount 1 will be amount 0 with the interest rate applied, minus 800. We can eventually expand the whole thing out because we know amount 0 is 60,000, and we come up with eventually an answer. Closest thing to extension 2 maths, I guess, that 2 would ever do, recurrence relations. There it is, right there. Calculate the amount of interest earned in those first 3 months. The amount of interest will be, so we've basically got the balance plus the withdrawals minus the principal. Whatever's left must be the difference is the interest that's been applied. How much money have we got in our account after the 94th withdrawal? So if we sub 94 in, basically it's again the same as the time payments. We've got the original amount compounded minus all of the withdrawals in this case. Sub it into our formula, and there we go. 187.85. There we go. You can see I've only picked 5 questions to have a look at.